Hey guys, welcome back. Hope that you had a good weekend. And if you celebrate it, happy Easter. This week we're doing 11.3, 4, and 5. So this is the first video for section 11.3, which is about the integral test and estimates of sums. Okay, so in general, like the slide says, it's actually really hard to find the sum of a series. Unless it's a very, I guess you could say, pretty looking series or something that we can compare something to. So in this section, we're exploring how to find the sums or how to determine possibly an upper bound for a sum. So we were able to find the sum for the series 1 over n times n plus 1 in a previous section because we could find a simple formula for each partial sum. I'm not sure if you guys remember that from 11.2. But like the slide says, again, this is sort of a special case. So let's look at a different type of series, 1 over n squared. So what you see on the screen is the first 5 terms in the series 1 over n squared. So we have 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. So that is what this sum looks like. 1 plus 1/4 plus 1/9 plus 1/16, and so on. There's not an exact formula to figure out what this sum is, but by using a computer, and don't worry, you won't be asked to do this, by using a computer, we can look at the larger partial sums. So this is S5, S10, S50, S100, 500, 1000, and 5000. And remember, S is a partial sum. So S5 means the sum of the first 5 terms. S10 means the sum of the first 10 terms, sum of the first 50 terms, and so on. So once you get up here to 5,000, that's pretty big. And if you look at the actual values in the second column, you can see that it does sort of appear like they might be converging to something. And the screen says 1.64. I would say probably something a little higher than that, right? Because this is continuing to go up as n increases exponentially. Okay, so you can confirm this by looking at the graph to try to understand what's going on if this were a continuous curve and not just the series. So this is the graph of 1 over x squared, and then the rectangles that we would estimate the area with using right endpoints underneath the curve. So the base of each of the rectangles is 1, and the height of each of the rectangles is the value of the function 1 over x squared. So why are we using widths of 1 for a rectangle? Well, remember, a series or a sequence is only defined at the integers, 1, 2, 3, 4, 5, and on up. So you can't look at what the values are in between the whole numbers. So we can only look at 1, 2, 3, and so on. So it does appear that these rectangles, the areas of these rectangles, would eventually get so small that they would no longer contribute to the sum of the series. Okay, so if we exclude the first rectangle, which has area 1, the total area of the remaining rectangles is smaller than the area under the curve. Why is that true? Because of all of this blank white space. Remember that depending on if the curve is increasing or decreasing, the estimate using rectangles like this is either always an overestimate or always an underestimate. And in this case, you can see it's definitely an underestimate. So the total area of the remaining rectangles is smaller than the true area under the curve 1 over x squared, if you look greater than or equal to 1. Well, what is the value of that integral, or that area, from 1 to infinity of 1 over x squared? We've actually looked at this one before in 7.8, and this integral is convergent and has a value of 1. So if you knew that the area from 1 to infinity of this function is 1, and the area of that first rectangle is 1 itself, then that means this area 1 plus all of the area under the curve all the way to infinity is 1, then 2 would be an upper bound. So like this says, the picture shows that all the partial sums would be less than 2. 1, which is the first rectangle, and 1, which is the improper integral of the curve. So the partial sums are bounded by 2. We also know the partial sums are increasing simply because every single term in this series is positive, so it continues to get bigger as n increases. Therefore, by the monotonic sequence theorem, the partial sums must also converge. Therefore, the series converges. So we're absolutely sure the series 1 over n squared from 1 to infinity is convergent, and we just found that it's definitely less than 2. Okay, now to look at a different series, 1 over square root of n. This is going to grow slower than 1 over n squared would, and we have listed out here the first 5 terms of the series again. Again, if you use a computer-generated or computer program to generate the partial sums at the same values that we looked at in the last series, then you can see it doesn't really look like these numbers are slowing down. In fact, there seems to be no pattern at all, except that it continues to grow no matter how high n reaches. There's no convergence like there was in the last one. So I would say an initial gut reaction would be this is absolutely divergent. So let's look at the picture again. This is the 1 over square root x. And if you look at the left-hand endpoint and create rectangles like we did when we were estimating integrals, then we can do the similar sort of comparison by looking at the integral. Why are we using the left endpoints this time instead of the right endpoints? Well, we want to find something that's too big, because our suspicion is that it's divergent, not convergent. So here, again, we have rectangles where the base of each rectangle is 1 and the height of each rectangle is the value of that function at the left endpoint of the interval. So the sum of all the rectangles would be the 1 over square root of n from 1 to infinity. And this total area should be greater than the area under the curve. As you can see in the picture, all these rectangles would be an overestimate for the true area under the curve from 1 to infinity. So we look at the improper integral 1 over square root of x from 1 to infinity instead. But again, from 7.8, we already know that this integral is divergent. Okay, and what that tells us is that we have an integral, an area under the curve that is divergent, and we know that our series is larger than that. Again, these rectangles are larger. So we found something smaller that's divergent. Therefore, our larger series, by default, must also be divergent. Okay, so what did we just do? We just did 2 examples of something called the integral test. Suppose f is a continuous, positive, decreasing function from 1 to infinity, and let a sub n equal f of n. Then the series with that same function is convergent if and only if the integral is convergent, meaning it goes both ways. So part I says if the integral from 1 to infinity of f of x is convergent, then so is the series. And then the opposite, if that integral is divergent, so is the series. So this is a very powerful test, because instead of worrying yourself with what the sum of your series is, you can switch over to looking at the improper integral, which is something that we've already covered again in section 7.8. So an example. Test the series 1 over n squared plus 1 for convergence or divergence. So of course, we're going to use the integral test that we just learned and evaluate that integral instead. So remember, to use this, your function has to be continuous, positive, and decreasing from 1 to infinity. So if you take a look at the graph of 1 over x squared plus 1, you can confirm that from 1 to infinity, that function is continuous, positive, and decreasing. So we can definitely use the integral test. So we set up the improper integral from 1 to infinity of our function 1 over x squared plus 1. And remember, the way we handle this is by replacing infinity with a parameter t and adding a limit out front. That way we have a regular proper integral 1 to t, and then we deal with the infinity part later using a limit. So 1 over x squared plus 1 just happens to be the derivative of the inverse tangent. That's not something I've asked you guys to memorize in the past, so don't worry too much about that, but it is in the list of integrals and derivatives in the back of your book. So 1 over x squared plus 1 becomes tan inverse of x. And then once we apply t and 1 from the limits of the integral, we have tan inverse of t minus pi over 2, because tan inverse of 1 is pi over 2. Now we have something we can apply the limit to. What's the limit of the tan inverse of t as t approaches infinity? And then pi over 2. So when you apply this limit, if you look at the graph of tan inverse of t, this will help you understand what's happening here. But ultimately, this ends up being pi over 4. So what did we just find? We found that the integral of 1 over x squared plus 1 converges. It has an actual answer. It's not divergent. Therefore, by the integral test, because this integral is convergent, so is the series. So the series is convergent. All right, next up, look at something called the p-series. This is very, very, very common. You've already seen this when we were talking about limits, where you had 1 over x to the r. So the series, the sum from n equals 1 to infinity of 1 over n to the p, is called the p-series. Series for obvious reasons. P is the exponent of the n. The p-series is known to be convergent as long as p is bigger than 1, and it's divergent when it's 1 or less. And this is a fact that you can use from now on. Anything that you can make look like a p-series, you don't have to prove anymore. It's definitely convergent as long as p is greater than 1, and definitely divergent as long as p is less than or equal to 1. So an example of a p-series would be 1 over n cubed. So 1 over n cubed is a p-series with p equals 3. And because 3 is bigger than 1, using our rule, then this series is convergent. And then the opposite, 1 over n to the 1/3. 1/3 is less than 1, so this is a p-series where p is 1/3. Therefore, this series is divergent. And that's the end of the first video.